This is assignment 4, dining philosopher's problem, and we are going to show you how exactly we are giving the input in the command line. Okay, Dimitra, start the command line input. Press enter. So yeah, so we put command and enter, and now I will focus towards the actual Z board.
So what we see now are the 4 LEDs which represent the philosophers. The idea of this problem is to implement a solution for 4 philosophers which are sitting circularly at a table and have forks which are resources in between them on the table. Eat, think, then wait to get resources, and then eat, think again. The resources are forks. Each philosopher needs 2 forks for eating. He can start eating only when he has both forks. The blinking, like here, means eating. Solid on is thinking. These 2 are eating. Off means waiting for resources. We must resolve a deadlock problem, which we will describe shortly, and we must ensure that no 2 philosophers can get access to the resources at the same time. Therefore, no 2 adjacent philosophers can eat at the same time, and we observe this by observing that the 2 adjacent LEDs do not blink at the same time. The resources are controlled, managed by mutex variables, and the mutex variables are not the resources themselves. This will be also highlighted in the code in a separate presentation and report. The philosophers themselves are implemented as threads which run in parallel and follow a sequence of eating, thinking, and then waiting for resources again, and then repeating. So in one of the requirements of the problem is to make sure that the resources are only taken in use by 1 philosopher at a time. One resource cannot be used by 2 philosophers. This is implemented by a mutex variable and the lock and unlock. Another condition that we have to avoid is a deadlock. A deadlock condition would occur when all philosophers first select a resource on their left. If that would happen, then they would all be waiting for the right resources, which are actually taken by another philosopher on their right. So, in order to avoid this deadlock, we implemented a rule where philosophers have to pick their 2 forks in an order. We use the pre-indexing of the resources, the forks, in such a way that due to the circular arrangement, one of the philosophers will have to first pick his fork on the right, while the others will have to first pick the fork on the left. In this way, we avoid that deadlock situation, and we can visually observe that by noticing that throughout the observed run, we never see all the LEDs off at the same time. This again will be commented in the code, and we will have that separately in a report. So now we can see that another thing that we have to know, we have to outline is that the thinking and eating times are between minimum and maximum. In this case, as we saw on the beginning frame, it is between 100. The eating is between 100 milliseconds and 10 seconds. Thinking is between 1,000 milliseconds and the 10th seconds. We have to enforce that. So now here we can see the blinking again. All this time we never saw two adjacent LEDs blinking at the same time. We never saw all the 4 LEDs off at the same time. So we can see, for instance, one of them is eating, this is thinking, these are waiting. These times are random again. 2 are eating, they're not adjacent. They are eating again, these are waiting. And this finished eating, this now, the other 2 were eating at the same time, but one finished. In any case, we never see 2 adjacent blinking at the same time. So I think this sort of shows the
clear implementation of the philosopher problem.
The complying implementation according to the requirements of the problem, and due to the randomness of the range of values for the random times for eating and thinking, we see a certain pattern that it never repeats, and we also sometimes can have all the philosophers thinking at the same time, which we observed a few times. All LEDs were solid on.
Okay.
So I think this sort of concludes our video clip, and we'll complete this by a separate report.
Thank you.